If anybody here needs no introduction, it's our next speaker. That's what Cyrus Taylor said yesterday, and although he meant it, he went on to introduce him anyway. So I won't tell you again all his awards and accomplishments. Instead, I'll say that Brian Lynn and I knew that if Steve would come to this event, so would many of you. So I emailed Steve to say that we wanted to organize a symposium to celebrate the Standard Model 50 years after his landmark, a model of leptons. When he said yes, he would come, I knew that our work on the one hand had been made much easier, but now we had to actually do it. Steve, I can't tell you how many people said that they were coming because you were, nor how many people wished that they could have come because you would be here. We are gathered here to celebrate many important contributions to the Standard Model, but we're gathered here today because it is approximately 50 years after the publication of a model of leptons. Please welcome Steven Weinberg to tell us about the conceptual basis of the Standard Model.
Very grateful to you and the other organizers of this for organizing this meeting. On a purely personal basis, I've learned a tremendous amount from these talks and enjoyed it, and I have a lot to think about now in the weeks to come. I think that's probably true of all of us. Also, I have the honor of preventing you all from having your lunch. I'm going to reminisce about how the Standard Model emerged out of a welter of confusion and misconceptions and misunderstandings. Part of my talk will be a little autobiographical because no one knows better than I do how confused I was. But I suspect much of my confusion was generic. Some of those of us who started doing theoretical physics research in the late 1950s felt a sense of envy of our predecessors. Feynman, Schwinger, Tominaga, and Dyson in the late 1940s had figured out how to do calculations in quantum electrodynamics maintaining manifest Lorentz invariance. And that allowed them to sort out the infinities that were long known in these theories since the early 30s and show that they could all be absorbed into a renormalization of the parameters, charge and mass, and fields of the theory. And in this way, they were able to calculate quantities like the Lamb shift and the magnetic moment of the electron with a precision and an accuracy that was unprecedented in all of science. Beyond that success, what impressed some of us was that the program of renormalization provided a rationale for the simplicity of the version of quantum electrodynamics that they were using. The symmetries of quantum electrodynamics, Lorentz invariance and gauge invariance, by themselves were not enough. They would allow you, for example, to add terms to the Lagrangian that would allow the magnetic moment of the electron to be anything you liked, wiping out the possibility of doing a calculation. It was only when you impose the condition of renormalizability that you were forced into the very simple theory in which you could do these, not only could you do these calculations, but the results would agree with observation. Now, I don't think this aspect of renormalization theory was widely enough appreciated. After all, scientists have always, when they have a new idea, tried to find a simple manifestation, a simple theory that embodies the idea, and then work out the consequences and compare them with observation. And that's, of course, a good strategy. And I remember Oppenheimer grumbling that all this business about renormalization was just sweeping the infinities under the rug. But once you have a theory that works and is very simple, you're not done. The simplicity needs explanation, like everything else. And renormalizability provided such an explanation. Some of us felt it would be great to follow in the same path. That is, have a theory with more fields, more forces, more symmetries, perhaps, and use such a theory with the condition of renormalizability to pick out a simple version to account for all the data that our experimental friends were pouring out in such large quantities. But it was clearly going to be very difficult. We had a quantum field theory for the weak interactions going back to the work of Fermi in the early 30s, involving an interaction which was a product of two currents, originally just vector currents, and then through the work of Marshak and Sudarshan and Feynman and Gelman adding axial vector currents. But this theory was hopelessly non-renormalizable. It gave very good account of beta decay in the lowest order approximation, but could not be used beyond the lowest order of perturbation theory. On the other hand, we had many perfectly renormalizable quantum field theories that we could imagine for the strong interaction, vast numbers, in fact, and they could be renormalizable. Well, there was no rationale for any of them, and in any case, they were useless. You couldn't do perturbation theory because strong interactions are strong. Also, the experimentalists were adding to our problems by discovering more and more new particles at accelerators like the Bevatron, and leaving us with the puzzle, which, if any, of these particles are elementary, whose fields we should build our theory out of. Maybe the true fundamental quantum field theory has elementary lambda or sigma hyperons and K mesons, or who knows? This situation led, I think, well, in fact, I remember, to a widespread sense of disenchantment with quantum field theory. And a number of theorists, Jeff Chu in particular, adopted what I would call a positivistic philosophy. That is, that we should only deal in our theories not with things like quantum fields, which are purely mathematical, but with observables like S-matrix elements, and rely on the analyticity, unitarity, and Lorentz invariance of these S-matrix elements, plus whatever other symmetries there might be, to derive conclusions. In a sense, this philosophy has been revived in recent years in effective quantum field theory, but in its original form, it was hopeless. And if only because complex variable analysis is incredibly difficult when you have a lot of complex variables. It's just too hard. Anyway, it was too hard for me, and as far as I could see, it was too hard for my colleagues. All of us agreed that if you couldn't figure out the dynamics, at least you could do useful work considering principles of symmetry. Many new symmetries were being discovered, but there was something very puzzling about them. For example, isotopic spin symmetry was known Since 1937, when it was discovered that the proton-proton nuclear force is the same in a given spin state as the proton-neutron force. But this symmetry between protons and neutrons only applies in the strong interactions, not the weak or the electromagnetic. Gelman and Neyman pushed beyond isotopic symmetry and proposed the eightfold way, but that's not even exact for the strong interactions. Parity and charge conjugation and strangeness conservation. With strangeness, it was obvious. With parity and charge conjugation, it took the work of Li and Yang and Wu and Feynman and Gelman, Lederman, and Weinberg and others to show that parity and charge conjugation invariance also, along with strangeness, were only symmetries of the strong and electromagnetic interactions, but not the weak interactions. What's going on here? If symmetries are fundamental principles of nature, something built into the structure of nature at the deepest level, how can they only be partial symmetries or approximate symmetries? And if symmetries are not fundamental, then what are they? A new idea came in 1960, which at first we hoped might clarify this, although it didn't really. This was the idea of spontaneously broken symmetries. It was introduced by physicists, especially Goldstone and Nambu, who had experience with broken symmetry in condensed matter physics. The idea, of course, as everyone knows, is that you can have a theory where the equations have a symmetry, but the solutions, that is, the actual physical phenomena, don't respect the symmetry. Through some of the work of Goldstone and Nambu, and then in a theorem announced in 1962 by Goldstone, Salam, and me, cold water was thrown on this by the conclusion that for each spontaneously broken exact symmetry, you had to have a new massless particle, often called Goldstone bosons or Nambu-Goldstone bosons, which seemed to be a no-go theorem for this whole idea of broken symmetry. In 1964, an exception was pointed out by Broud and Anglaire, Higgs, Guralnik, Hagen, and Kibble, that the theorem really should say you get a massless particle for each broken exact global symmetry. Our theorem did not apply to symmetries that are local in the sense that the symmetry transformations can vary from point to point in space-time. In theories such as the Yang-Mills theory, which is a theory based on a local version of isotopic spin symmetry. Yang-Mills theory had been disfavored by physicists because it predicted zero mass particles like the photon, one for each local symmetry. But now the work of these authors in 1964 showed that for each broken local symmetry, the massless spin zero particle that you would otherwise have becomes the helicity zero part of a massive spin one particle. This is the famous Higgs mechanism. It's surprising in retrospect that the Higgs mechanism was not used by its discoverers, or at first by anyone else, to try to construct a realistic theory. As Toft told us, Veltman thought this was all just mathematics and not really relevant to physics, if I understood Gerard correctly. But also, I think another contributing factor to the lack of response to the Higgs mechanism was that at just that time, spontaneously broken approximate global symmetries, in particular chiral symmetry, SU2 cross SU2, which is just isotopic spin, but with independent isotopic spin transformations on the left and right-handed parts of the nucleon, or as we would say today, the quark fields. The spontaneously broken chiral symmetry turned out to be tremendously successful. This originally took the form of what's called current algebra, the study of the currents of the axial vector and the vector currents of the weak interactions, and particularly the exciting result of Adler and Weisberger, which gave a sum rule for these currents. Actually, for the matrix, one nucleon matrix element, or the commutator of these currents. But gradually, we realized that you don't have to think about currents, that this is the idea of a spontaneously broken chiral symmetry stands alone as a property of the strong interactions, having nothing necessarily to do with the weak interactions. This symmetry of the strong interactions led to calculations of properties of low-energy pions, which were experimentally successful. These were really the first quantitative strong interaction calculations theorists were doing, other than dispersion relations. And I think this largely killed off the S-matrix program. The practical analysis of the S-matrix program relied on low-energy pion interactions being strong, the so-called strip approximation, which I bet no one in this room remembers. But these new calculations based on spontaneously broken chiral symmetry showed that low-energy pion interactions are weak. Now, being a little personal, I continued studying the currents. That was by now a time-honored tradition. I studied the currents of the weak and electromagnetic interactions, wrote down sum rules, like the Adler-Weisberger sum rule, but taking the vacuum expectation value of the current commutators instead of the one nucleon expectation value, derived sum rules and counted particles like the particles I identified as the rho meson and the A1 meson. And then there were some interesting relations among them I tried to understand by considering a quantum field theory in which the chiral symmetry was made into a local symmetry. And of course, I immediately encountered the Higgs mechanism. What I had called the A1 meson, the positive parity spin 1 particle, became massive in this theory. But in accordance with a remark of Tom Kibble, the rho meson, which was associated with the symmetry of isospin, which was not spontaneously broken, remained massless, which didn't look like a very good agreement with observation. At some point, I realized that I was working on the wrong problem. Maybe what I should be working on are the weak and the electromagnetic interactions, of course, with different fields and symmetries, and where instead of getting a massive A1 particle, I would get a massive W particle. People have been talking for years about the current interaction and the weak interactions being mediated by a massive spin 1 particle, which was called the W particle. And with a massless photon, instead of what I had encountered, the massless rho meson. I had no clear idea about the strong interactions at that time. Even the quark idea, which was well known, was dubious. Murray Gell-Mann even was beginning to make noises about quarks not being real particles, but just being ingredients in a current algebra calculation. So, and it's for that reason, not because I wasn't clever enough to really worry about the flavor changing effects. But it was just the fact that I didn't believe I understood anything about strong interactions that I decided to make this just a model of leptons. Once you limit yourself to the known leptons, a left-handed neutrino and electron and a right-handed electron, the symmetry group became essentially inevitable. And I found later that, in fact, the symmetry group SU2 cross U1 was the same that had earlier been used in a slightly different way by Glashow and by Salam and Ward, but of course without the idea of spontaneous symmetry breaking. To break the symmetry, well, of course you could break the symmetry adding scalar fields of any kinds which are non-neutral under SU2 cross U1 and give them expectation values, and that would give masses to the W and Z. But if you also want to give mass to the electron and the muon, what you have to do is to add doublets of complex scalars. So I added one doublet of complex scalars. I found, in accordance with the Higgs mechanism, that a doublet of complex scalars is 4 real fields. 3 of them gave mass to the W plus, the W minus, and a neutral particle that I call the Z. And the 4th is left over. It's a neutral scalar particle that later became known as the Higgs boson. Abdus Salam independently developed essentially the same theory and published it just a little later. Both Salam and I, in our published papers, guessed that this theory was likely, in fact, to be renormalizable, but we didn't prove it. I can't speak for Salam, but I can remember precisely why I was not able to prove this. And by the way, when I do something stupid in our home life, my wife often points out to me, yeah, but you didn't renormalize your own theory. Now it all comes out. My problem is that I was using the only method for dealing with gauge theories that I understood, and that is operator methods, where you impose, in order to do perturbative calculations to derive Feynman rules, you need to choose a gauge in a gauge theory. The only way I knew how to choose a gauge is to impose conditions on the field operators themselves, like the Coulomb gauge condition, for instance, that respected the unitarity and the particle content of the theory. No one in the last 50 years has been able to show the renormalizability of these theories using those methods. The way to do it is with path integrals and the functional formalism of gauge theories. Unfortunately, at Tufts knew about this, as I did not. Faddeev and Popov, a little earlier, had worked out the general formalism without any specific application. I think probably without the application to spontaneously broken theories for the functional, well, what do you call this? Well, for this approach, the path integral approach to choosing gauges in gauge theories, he invented a Lorentz invariant gauge for spontaneously broken gauge theories, and outlined an argument for the renormalizability of these theories. The proof of renormalizability was completed by a Tufte with his teacher Veltman, and also independently by Ben Lee and Jean Saint-Justin. This introduction of path integral methods had an importance beyond renormalization, important as that was. In the subsequent decade at Tufte, and Sidney Coleman and Polyakov used these methods to identify non-perturbative effects in quantum field theories that you couldn't find any other way. The electroweak theory, apart from that, although it turned out to be very important in the development of the Standard Model, apart from that, the electroweak theory was now regarded widely as a very interesting theory. Quarks were put into the theory, theoretically. A search for neutral currents was undertaken, and they were found at CERN. After a certain kerfuffle, the properties of the neutral currents were found. Wise described this in his talk. They were found in an experiment at SLAC to agree with the standard, with the standard electroweak theory, and we now had one part of the Standard Model. I think after this experiment at SLAC on the parity violation in the neutral currents, the acceptance of the electroweak theory was pretty widespread. It wasn't long before the other part of the Standard Model was discovered. Glenn, what time nominally am I supposed to end? 12:50. Oh, I have some time. And your lunch is going to be delayed even more. The breakthrough, of course, was the calculations by Gross and Wilczek and Sidney Coleman's student David Politzer that showed that the coupling constant in theories of the Yang-Mills type, gauge theories more complicated than just electrodynamics, decrease with increasing energy. This immediately explained the scaling, called Bjorkane scaling, that had already been observed in a famous Friedman-Kendall experiment at SLAC. But I think even more important than agreeing with observation, this offered the possibility for the first time of doing calculations using perturbation theory to test theories of strong interactions. And Gross and Wilczek, and I believe Politzer, proposed a specific theory that we now call quantum crumb dynamics, in which the gauge symmetry is SU3, and the quarks come in 3 colors. In their first papers, Gross and Wilczek and Politzer, presumably with the Higgs mechanism in electroweak theory on their mind, proposed that the Higgs mechanism, perhaps due to dynamical effects rather than elementary scalars, makes the gluons heavy, which explained why we've never seen the massless gauge particles of Yang-Mills theories. Very soon, however, after that, both Gross and Wilczek and I proposed the alternative that the SU3 gauge symmetry is not spontaneously broken by scalar fields or dynamical effects or anything else. The gluons are massless, And we don't see them because just as the strong interactions become weak at short distances, they become strong at long distances, and the quarks and also the gluons and also the quarks, any particle with color is trapped and can be never isolated as an independent theory. This was tremendously attractive and successful. There was an aspect about it that I found particularly attractive, and still do, I think particularly appealed to me. And that is that if you have quantum chromodynamics and you don't add anything to break the symmetry, no new scalar fields or anything else, and you impose the condition of renormalizability, just as our forefathers did in quantum electrodynamics, then the theory is so simple that it can't violate the conservation of flavors like strangeness. So, in other words, just to take this example, the fact that strangeness is conserved in the strong interactions and not in the, also the same is true in the electromagnetic interactions, but not in the weak interactions, doesn't require any special explanation. It's broken in the weak interactions because it's not a fundamental symmetry at all. It's just an accidental consequence of the simplicity imposed on QCD and QED by the symmetries of those theories, the exact symmetries, the gauge symmetries, and renormalizability. With small up and down quark masses, the same is true, at least approximately, of isotopic spin symmetry and chiral symmetry. And also, it's true of charge conjugation invariance. The reason that's violated in the weak interactions is because there was never any reason why it should be conserved. It's just an accidental property of the QCD and QED. It's almost true of parity. It's true perturbatively. There are non-perturbative effects which need special treatment, as discussed here by Helen Quinn. That was provided by the work of Quinn and Pache. This was a real aha moment, in the sense that things that you've known about for many years suddenly become explicable. You understand why they're true. They're not just experimental facts. So we now had the standard model, that is the electroweak part and the strong part, with the big outstanding question: how is the gauge symmetry, the SU2 cross U1 symmetry of the electroweak theory spontaneously broken? One could follow either in the path of Goldstone, who had studied spontaneously broken symmetries in 1960 by adding scalar fields and letting some of them have vacuum expectation values just coming out of the dynamics of the theory. And that's what Salam and I had done, adding this doublet of scalar fields. Or we could follow in the path of Nambu, also 1960, who had never introduced scalar fields in his theory of spontaneous symmetry break-in, but imagine that chiral symmetry was broken by the strong force acting between nucleons and antinucleons. And that path, imagining the electroweak symmetry is spontaneously broken by new, strong dynamical forces. QCD couldn't do it. We had to introduce new, strong forces. That was developed in the late 70s by Lenny Susskind, and independently hedging my bets, me. And when we introduce this idea of Technicolor, which in some ways is still, I think, more attractive than reality. The issue was settled, of course, as everyone knows, by the discovery of the Higgs boson, which turned out to be the leftover member of the quartet of real scalar fields that Salam and I had introduced. So we now have the standard model, which is tremendously successful, and we're very happy with it, and we're celebrating it. And in addition to its account of known physics, you can regard it as a triumph of quantum field theory as a fundamental underpinning for the laws of nature. Or maybe not. Since the late 1970s, we've come to understand that within pretty broad limits, any theory that satisfies certain very general conditions will look like a quantum field theory, what we call an effective field theory, at energies below some mass scale I'll call capital M. This is the same capital M that was in Mike Peskin's talk. This is a folk theorem. I think Goldberger introduced this term. A folk theorem is something that's certainly true, but no one has managed to prove it, but is universally believed. The trapping of color in quantum chromodynamics is another folk theorem. This actually comes out of experience with many individual theories, specifically in condensed matter physics in the work of Ken Wilson. So it's quite plausible, and most of us, I think, now think that the standard model is indeed an effective field theory, which works well because we are studying energies much less than this scale, capital M. You can apply this general idea to it in a number of contexts. In some contexts, the symmetries of the theory don't allow any renormalizable quantum field theory at all. In that case, the leading term, when you do calculations, is just the tree approximation built out of interactions which are of the lowest order in 1 over m. And then you get corrections from loops. You can do loop calculations in this kind of theory, and they have infinities in them, of course. And there are also interactions of higher order in 1 over m, and they have counter terms that can cancel the infinities in loops. I like to say that non-renormalizable theories are just as renormalizable theories, but in this sense. This actually started effective field theories in elementary particle physics. It started with the study of soft pions, where we developed effective field theories for soft pions interacting, if you like, with nucleons, based on the spontaneously broken chiral symmetry. There's no renormalizable theory of these soft pions, but the scale m for these theories is about 1200 MeV. General relativity itself is, I think, the leading term in such an effective field theory, where m is something like the Planck mass, 10 to the 18 GeV. And the fact that Einstein was correct in throwing away all higher derivative terms like R² terms, for instance, in the action of general relativity, is just that they are multiplied by powers of 1 over m and hence negligible. Not only negligible if you do astronomy, but negligible if you do experiments at any distance scale much longer than the Planck length. On the other hand, there are other cases where the symmetries do allow a renormalizable quantum field theory. In that case, the leading term is the renormalizable quantum field theory, including terms of all orders in the dimensionless couplings. There are corrections to be expected, why not, which are given by powers of E, the energy you're studying, divided by m, this fundamental scale. And the extremely important point is that these interactions can violate the symmetries of the renormalizable theory, which were not fundamental, like strangeness conservation, for instance. They were never fundamental at all. They were just accidental properties of the theory with the simplicity imposed by renormalizability. Once you start including non-renormalizable corrections, there's no reason they should respect those symmetries. I think most important is the fact that the whole renormalizable standard model is too simple to violate baryon and lepton conservation, at least perturbatively. There are non-perturbative effects discussed by Atoft and others at this meeting, by Rocky Kolb in his talk about cosmology, which are potentially quite important, but are negligible in accelerator experiments here on Earth. The non-relativistic corrections can violate lepton conservation. Well, I should have restricted that remark to baryon. Baryon violating interactions are of order 1 over m², which makes them very weak. They may show up in proton decay, but no one has seen that yet. The lepton violations are only of order 1 over m. I mean, they're only suppressed by 1 power of 1 over m. They can, and in fact we see they do, produce masses of neutrinos. If m is of the order of the grand unification scale at which the 3 couplings that, as Georgie Quinn and I showed, come together or approach each other at some energy of the order of 10 to the 15 GeV, if that m is of that order of magnitude, you get roughly the right neutrino masses, although this has certainly not settled down. CP is another one of these accidental symmetries. Now, CP is violated, CP conservation is violated in the standard model, even the renormalizable theory, because you, as someone pointed out at this meeting, because you have 3 doublets of quarks. If you only have 2, it could not be violated by a renormalizable standard model in perturbation theory. The mixing between the 3rd family, the top and bottom, with the first 2 families is weak, and that's why CP violation is weak. And in fact, it took some effort to realize it was there. And again, the higher order in 1 over m corrections, there's no particular reason why they would even approximately conserve CP. As Rocky Kolb's talk showed, the consideration of these 1 over m corrections is a good way of analyzing the possibilities beyond the Standard Model in cosmology for things like baryon synthesis. But I'd like to emphasize that this is really generic. Once you adopt this effective field theory mindset, you expect baryon, lepton, strong violation, strong CP violation from any correction to the renormalizable Standard Model. Well, I am now out of time, so let me just say a few more things. I promise not more than 5 minutes. We now are left with the question, what theory describes nature at the scale m? These effective field theories are very nice. You can do calculations in quantum gravity to your heart's content, but the theory loses all predictive power if you try to use it at energies approaching m. And for that, you really need to know what the true theory is. Just as in the strong interactions, you can do calculations of soft pions as long as you stick to energies below 1200 MeV, but if you want to go beyond that, you need an underlying theory, which turned out to be quantum chromodynamics. In the real, well, more generally, if you want to do calculations that go beyond the Standard Model, you can do effective field theories, but if you want to push the calculations up to energies of the order of m, whatever m is, you really need to know what, which I'm guessing is something around the gut or the Planck scale. You really need to know the underlying theory at that scale. It may be a quantum field theory, maybe a grand unified theory, maybe an asymptotically safe theory, maybe a supersymmetric theory, or it may be not a quantum field theory. Everything we've learned about the Standard Model doesn't reassure us that the fundamental theory is a quantum field theory. Maybe it's a theory with a multiverse. Maybe it's a theory that's quite different from string theory, from quantum field theory, like string theory. String theory may look like quantum field theory in some aspects, but it's still, the underlying theory is very different from quantum field theory. Maybe it's not even a theory based on ordinary quantum mechanics. We don't know. The young theorists who are starting research today may envy the excitement and delight that those of us in this room experienced in developing the Standard Model. But I hope that that envy is misplaced, will turn out to be misplaced in the same way that our envy, or my envy if you like, of the physicists of the late 1940s turned out to be misplaced. Because the young theorists who are starting now have a chance to take the next big step beyond the Standard Model. Savas beautifully described some of the directions this might take. Maybe they'll be able to go all the way to the highest energy scales, M, where the final theory will be revealed. Thank you. Yeah, sure.
We have time for questions.
I want to make 3 very brief remarks. One is, I think you have been very kind to Salam. Of course, he did have the same ideas and the same idea about spontaneous symmetry breaking, but he tried to make a theory without U1, just as U2, and to putting the, at least if you look at his publications, he is putting the electron, the muon, and the neutrino into a triplet representation.
I'd have to look back at that. My recollection, I mean, his talk at a Nobel symposium is always the article that's quoted, and I was pretty sure that that had SU2 cross U1. I'll check that. I'd be surprised.
But
he may very well have had an earlier paper with just SU2, which I'm not aware of. But that's quite possible.
Well, he put all the electron, the muon, and the neutrino into a triplet, and that
well,
would
that's not
work.
what I remember of the paper. But I'll look it up.
Okay.
Thank you.
The other remark is there are more precursors of QCD. In particular, you could have mentioned Gell-Mann, Fritsch, and Lloyd-Wheeler, who nearly had it right, except they didn't know about asymptotic freedom.
Well,
so,
yeah, I would say that asymptotic freedom was the turning point. I think that's right. There are other people who, it's quite right. I think there was also oh God, well, in a sense, Wally Greenberg and others.
And Hanne Nambu would be the other name.
Yeah, that's what I was thinking. Right, that had the idea of a gauge theory with coupling to a color that took several values, because there was the old problem in the quark model of how you get 3 fermions into a state where the wave function looks symmetric between the 3 fermions, and the answer is it's anti-symmetric in the color. That was the point of Wally Greenberg. Yes, all those were precursors. You're right, and maybe I should have mentioned them, but I still think that for me it was asymptotic freedom that made all the difference.
Right. No, I remember that I saw this paper and I knew about asymptotic freedom, so I thought, I know the answer to your problem.
Yeah, you actually did a calculation that showed the asymptotic freedom. I believe you announced it at a conference, but did not publish it at that time.
That's right.
And therefore, it had no impact on on people like me who were not at that conference.
The other thing I want to mention, just as one very typical aha moment, that was the discovering of the instanton effects, which make the eta particle stand out, more massive than the pions and
the U1 problem. There has been this U1 problem.
It was a lovely moment that because this problem was with us for years about the eta particles. Why are they so different from the vector particles?
Right, I agree. I mean,
then suddenly everything fell into place.
What Gerard is saying, for those of us who are here who are younger, if you just look at this kind of theory, it looks like there is a U1 gamma 5 symmetry. And that has to be spontaneously broken, because otherwise lots of particles would be massless. And where is the Goldstone boson? Well, the particle with the right quantum numbers to be the Goldstone boson of that is the eta. And the eta is not only not massless, but it's beautifully given, its mass is beautifully given by the Gell-Mann-Okubo sum rule. And that the answer is there is no such U1 symmetry, and the reason is, as Gerard showed, that that current conservation is violated by anomalies, which then become things that you can't avoid because of the instantons. Yes, there's a lot that I didn't cover in my talk.
In his Nobel talk, Salam actually does not have SU2 cross U1. What is ironic that in 1964, with Ward, he actually had exactly the SU2 cross U1 Glashos. It was without the Higgs, as you know.
Yeah.
And you know, they used to say, at least that's what he told me privately, they never knew about Glashos' paper. Simply, it seems that the referee didn't know in 1964.
Well,
but
yeah,
talk,
I don't think...
But in the talk, somehow he didn't have SU2 cross U1. He didn't have your simple model of leptons, okay? I think that we could
I thought he did, except for the spontaneous symmetry breaking with Ward in 1964. Are you saying that's not correct?
Well, in 64 he had an SU2 cross U1, but he wasn't Higgsed.
Yeah, of course. It didn't have spontaneous symmetry.
In the Higgs case, he didn't have it.
And the same was true of Glashow a little earlier.
Okay.
I didn't know when I did my work in '67 about Glashow or Salam and Ward at first. And in fact, there's a version of my paper which surfaced recently, and Frank Close has published a photocopy of it which doesn't quote Glashow. And it wasn't because I was trying not to quote him, but because I just didn't know about it until, fortunately, before my paper was published, I stuck in the reference to Glashow because I had found out about it.
Well, actually, what I have a question and a comment, if I may. A question that's been bugging me recently, more and more, is that when it boils down to the gauge series spontaneously broken be renormalizable, the main point is to restore the gauge freedom by adding another degree of freedom, just as in QED, which is the unphysical guy that got eaten. But that already existed in the work of Stuckelberg, we know today. What my question is, did you know of Stuckelberg's work when, or you just ignored it?
I have never been able to read any papers by Stuckelberg. I hope he's not alive.
No, he's not alive.
But you know, he did work on the renormalization group, which I found absolutely impenetrable.
Right.
So no, I don't know anything Stuckelberg did. I'm sorry about that.
No, you didn't know.
I hope he will forgive me looking down from heaven. But he was not, I mean, he may have been a great physicist, but he wasn't a great writer of physics articles.
So you didn't know? I mean, that was my question. You didn't know?
No, I didn't know about it.
Okay, one short comment, if I may. As beautiful as the idea of large scale is appealing in the case of grand unification, it may turn out that the M may not be so large. After all, it brings you the hierarchy problem. And as you know, the standard model is all about small couplings. So
yeah,
especially...
there's a problem. The nice picture of baryon and lepton non-conservation that I referred to, that we haven't seen baryon non-conservation in our laboratory because it's of order 1 over m squared, and we just barely see neutrino masses because they're of order 1 over m. That picture only works if m is very high. If m is something like 10 TeV, which in fact Rocky in his talk was considering, then you really have to impose all over again a separate condition of baryon conservation, because general interactions which have dimension 6, let's say, and are of order 1 over m, give you, if you don't impose some new symmetry, give you a hopelessly large rate of proton decay. So I think Rocky is right in looking for such effects, that is, effects in astrophysics that come from terms in an effective action that are where the m is intermediate. That's certainly worth doing. In fact, it's worth doing in a lot of contexts. But if such effects are discovered, we will have a new problem, which is why baryon number is conserved in those terms.
We have unfortunately come to the end of this symposium, and I want to take a few minutes to thank just a few people very quickly. First, not just to Professor Weinberg, but to all of our speakers who put down everything they were doing to come here for a few days and join us to celebrate the Standard Model and to look forward to the future. We had a number of sponsors, and I'm not going to go into all their details, but Richard Morrison, Mike Lubin, the Joseph and Nancy Keithley Foundation, and the Keithley Instruments, the Department of Energy for helping bring so many of the people who are here intended to sit in the back, but sometimes migrated up to the front, as well as other sponsors, John Martinchik, Brian Lynn, Patrick Alman, and Antarada, an anonymous donor who supported all these graduate students and postdocs. Mike Mitchell of Mitchell's Homemade Ice Cream. Many parts of the university, especially the College of Arts and Sciences and the Department of Physics, and Media Vision, who've been taping this, sending it out to the world, and also capturing it so it will remain, and we will be putting it up. And we will be taking all the talks and transcribing them, and Hirsch Matur will be emailing you saying, would you like this to be in the proceedings, or do you want to change it? As well as many of my colleagues. In particular, I want to call out Pavel, because he took over the chairing of the next meeting that's starting at 4 o'clock, if you want to stick around, leaving me to spend more of my time on this. Brian Lynn, who's I hope is watching, provided much of the original impetus and intellectual vision behind the symposium, and it's really unfortunate that he hasn't been able to join us in person. Kellen McGee served as the scientific secretary, Patricia Princehouse, many people from the office of the Dean of the College of Arts and Sciences, Tony London, Mike Scott ran our AMA. We have had 25 volunteers, and I'd love them all to stand up because they've been fantastic. But in particular, this gentleman over here, who should stay standing, because he organized just about everything, and I don't know how his supervisor let him do that. Finally, in an event, any event like this, there is one person who, of course, is standing way at the back in the corner, who toils away quietly without any fanfare. And I would like to have a round of applause for all the people who made this symposium, but most of all to Betty Gaffney from the Department of Physics, who did absolutely everything, then did it again when we needed to change it, and then did it once more. Thank you, Betty. And thank you to all of you for joining us. And I look forward to seeing you soon in the future. And I hope you will let people know about the videos that we're going to produce and the book, and you will help us produce this book. Thank you again, and safe travels home.